It's my pleasure to be here to share our research with you. What is this? Oh, that's fine. So I just wait. There we go. So before I start, I want to acknowledge all my collaborators, and this work won't be possible without this international collaboration. And I want to especially shout out for my advisor, Rob Sloan, senior scientist at Hui, and also your Matter, who is a pioneer in carbon mineralization, and finally engineer at Hui, Paul So, who was instrumental in collecting the data in Oman. This is actually showing them doing this on our site. Okay, now let's jump right into it. Peridotite is the main constituent of Earth's upper mantle and is one of the most abundant rock types in the solar system. And when it typically resides at the deep interior of planets, where it's high pressure and high temperature. In some rare cases, they can be exposed to the surface, where it becomes chemically unstable and prone to react with water and CO2 there. And these reactions have profound implications in many aspects of Earth sciences. But for this talk, I'm going to focus on their potential applications to subsurface energy systems. And so the reaction between peridotite and water is called serpentinization, and it can produce elemental or native hydrogen, which is a carbon-free fuel, and is thought to be a very important element in the energy transition. And as you have probably heard, there is different colors for hydrogen produced in different ways. And in this case, the natural hydrogen produced through serpentinization and other processes is termed white or gold hydrogen. And some people even propose that we can stimulate the production of hydrogen in those systems by fracturing the rocks and circulating water in the formations. And in that case, the hydrogen produced is usually termed the orange hydrogen. And the hydrogen can further react with the carbon in the formations to form CH4 methane through both abiotic and biotic pathways. And that's the reason why the gas mixtures observed in ultramafic formations is typically a mixture of hydrogen and methane. And so since people are getting more and more interested in harvesting the hydrogen produced in these pathways, obvious question to ask is, where do the gases go in these peridotite formations? And that's going to be the first overarching scientific question I want to address in this talk. And the second aspect of peridotite alteration in low temperature environment is its reaction with CO2, which is a carbonation reaction. And this reaction can essentially eliminate CO2 through the formation of stable carbonate minerals. And this has been proposed as a promising method to basically reduce the CO2 in the atmosphere to slow or hopefully halt a climate change. And these two reactions are both reactions between fluids and rocks, and therefore it requires a constant contact between the fluid phase and the rock phase. However, through the reaction process, the reaction products, namely the serpentines and the carbonates, will inevitably accumulate on the reaction surfaces, and that can gradually reduce the reaction rates and potentially halt the reaction. And that leads to a second question, that is, can the reactions stay active even with the production of these minerals? And that would potentially require a fracturing of the rock. And since both the carbonates and the serpentines have lower density and higher volumes, by somewhere from 30% to 50% than the peridotite. There is this popular theory that this volume increase can cause fractures in peridotite, which can enhance the permeability in these rocks. And this so-called reaction-driven fracturing can keep the permeability in these formations and eventually lead to the progression of these reactions to completeness. And this is the second scientific question I want to address in my talk. And so let's first look at what we know about the gas systems in peridotite formations. So there is limited knowledge about these natural hydrogen systems, and there are two theories about how gas transport and storage in these systems work. The first theory is the so-called short-term system, where the gas generated through active serpentinization is transported to the surface at a relatively short time scale, somewhere from 10 years to 100 years, and there is little accumulation in the subsurface. And the second one is called the long-term accumulation system, where the gas generated from the source rock is stored somewhere in the subsurface, and the residence time can be very long, either from it's on the order of thousands of years at least. And in this case, what you are observing on the surface is just a slow leakage from this gas storage. And obviously, these two systems are very different, but there is very little way to know which one is at work in peridotite formations. And so far, the primary ways to try to characterize these systems is through geochemical measurements of gas fluxes on the surface. And so one way to study, one of the best places to study these processes is the Somalia ophiolite in Oman, which is the largest piece of ultramafic rocks exposed on Earth's surface. It's in the Middle Eastern country, Oman. And so my colleague, James Liu, who is now a assistant professor in geochemistry at the Miami University in Ohio, went to the Somalia ophiolite and measured the gas fluxes in some of the hyperalkaline pools in the ophiolite. These hyperalkaline pools with pH typically higher than 12 are thought to be fed by active serpentinization reactions at greater depths. And here I'm showing the pool, and many of those pools have bubbles coming out of the floor, and they collected those bubbles and measured the composition of the gases as well as the gas fluxes. And this led to some estimation of both the methane and the hydrogen fluxes from these sites, as shown by the black bars here. And the y-axis are in log scales. As you can see, the gas fluxes are quite variable, and they can also differentiate between a diffuse outgassing, which basically means there's no visible gas bubbles, and also focused outgassing, which means that there is visible bubbles, as in the case of this photo. And using these observations and the assumption that the ophiolite is a short-term system, meaning that the gas that you observe on the surface comes from mostly active serpentinization in the subsurface, they get to a reaction rate or serpentinization rate of 10 to the minus 13, a maximum rate of 10 to the minus 13th per second. And this is the fraction of rock that reacts away per second. And using this number, a recent paper by Alexis Templeton, who is a famous geobiologist, came up with this number of 10 to the 4th fold of increase in reaction rate, which is required to make hydrogen production in Oman economic. This basically means that you have to dramatically increase the reaction rate by fracturing the rock and circulating water potentially containing catalysts through the fractures to increase the hydrogen production. They have also proposed this model where you have where there is a biological bloom in the shallow subsurface of the material of the ultralight, which feed on the hydrogen generated at depths. And they think that this probably consumed a great amount of the hydrogen produced through serpentinization. However, in some places, like the hyperalkaline pools, there may be gas highways through which the gas formed at the greater depths can be transported at much faster rate to the surface, which will prevent the gas from being consumed by the microbes. So the 10 to the 4th fold increase in reaction rate seems pretty pessimistic. And however, if you look deeper, you will see that some of the assumptions are quite questionable. First, we don't know that how representative are the surface gas fluxes that this model rely on. So as I said, this relies on the gas fluxes observed in the hyperalkaline pools, but those are just measurements conducted on the 5 or 6 hyperalkaline pools, and there's not much reason to believe that they represent the high end of the gas fluxes. And also gas seepage can also happen just on the dry surface without underwater. And in that case, it will be very difficult for you to even spot it. In fact, the hyperalkaline pools are the only places where you can see with your naked eyes that there is gas coming out of the ground. And so the surface gas fluxes themselves are probably not that reliable. And the second closely related question is how to get it migrate in the subsurface. And that's an even harder question to answer because there's no way to directly observe that. Especially we are interested in whether there are indeed these gas highways which can transport gas very efficiently from greater depths. And if that's true, then those are probably the places where you want to conduct the measurements and probably even drill for hydrogen if you want to harvest it. And finally, is there a reservoir in these systems? Because that will affect whether the hydrogen you measure on the surface can truthfully reflect the reaction rate happening at depths. And if there is indeed a reservoir in the subsurface, and what we're seeing on the surface is just a slow leakage from that reservoir, then you just can't use the gas flux to estimate the reaction rate. But if that's indeed true, then we probably just need to drill into those reservoirs and suck the hydrogen out of it. That will be probably the easiest solution, but still we don't know. So all these questions cannot be answered with the current observation or modeling techniques, and apparently new techniques that can potentially allow us to see gas transport in the subsurface is required. So now let's turn to the second question, that is whether reaction-driven fracturing can maintain the permeability in the peridotite formation. So the process of serpentinization has been extensively studied in the lab. Here I'm showing the work by my colleague Frieder Klein at WUI, in which they have conducted an in situ serpentinization reaction. So they basically soaked the meter scale sample of a fresh peridotite in seawater for a maximum of 1.5 years. And then they measured the overall volume change of the sample. And here they clearly show that there is a significant volume increase in the sample at the end of the experiment. And this volume increase is positively correlated with the experiment time. And more importantly, through this backscatter electron image, they have shown that there are fractures growing in the olivine crystals as shown here. And these are pretty clear evidence for the existence of a reaction-driven fracking, at least at the lab scale. However, we need to remind ourselves that these experiments are conducted on millimeter scale samples at a pretty high temperature of 300 degrees C. And especially this temperature is it's much higher than the typical peridotite formations that we can access through engineering methods. And those formations typically reside at a temperature of below 100 degrees C. So the question I want to ask is, how does this translate into a formation scale at a much lower temperature? And this also requires a few methods to observe these kind of processes. All right, so with these questions in mind, my advisor Rob Song and his colleagues went to the Somalia ophiolite in Oman, and specifically they went to the Oman drilling project Multi-Borehole Observatory to conduct the first ever seismic and borehole-acoustic experiment for understanding active serpentinization. The Oman drilling project Multi-Borehole Observatory was established through an international effort to study active serpentinization, and it drilled a few closely spaced boreholes on a peridotite terrain in the Somalia ophiolite. So here is showing the mafic and ultramafic formations of the ophiolite, and this is showing our study site and the high resolution satellite image around it. And I'm emphasizing this because, as you can see, we are located in a pretty remote area with minimum human activities. The closest permanent human residence is a small farm that is about 3 kilometers south of our site. I'm stressing this is because some of the seismic signals I'm going to show you later, some of the similar signals have been known to be generated by human activities, but we are very sure that ours are not. And we are going to show several lines of evidence for that. And this is what our study site looks like. This map is plotted on another high resolution satellite image. The triangles are geophones, 3 component geophones measuring ground surface velocities. And the 2 purple circles are the 2 boreholes, BA1A and BA1B. Those boreholes are about 400 meters deep. What Rob and his colleagues did was that they first deployed the hydrophones into the 2 boreholes, which were active for 9 months. The hydrophones had a spacing of 70 meters, and the shallowest one is at 30 meters. And the water table at the site is at about 15 meters, although it varies over time. And near the end of the hydrophone deployments, they further augmented the observation system by this array of densely spaced geophones. And the geophones were there only for 21 days. And another noteworthy fact is that the geophone array is very dense with a minimum station spacing of 5 meters. So as we'll see later, this small station spacing is pretty necessary for the kind of signals that we observe. And this is the picture of our study site. As you can see, there's just nothing there except for rocks and even not much vegetation because we are in a high desert. And this is looking, this is what you see standing at the borehole BA1A towards the other 2 boreholes. This is BA1A, BA1B, and BA1B, and they are drilled very nearby. And this is what the geophone, this is actually the instrument box and the solar panels on it, which powers our instruments. And the fence is for preventing animals from tampering on our instruments. There are, camels and there are herdsmen, in this area, and we actually saw their signals on our data. And the reason that I want to show you this picture is I want to reemphasize that there is no equipment that existed at our site other than our instruments. There are no pumps, no generators, and the site is not connected to the power grid. It's just in the middle of nowhere where they drilled a few boreholes, and that's it. everything is passive, and all the instruments were powered by the direct current supplied by solar panels. Okay, so with all those background, I'm going to talk about the piece of evidence that I'm going to talk about first are gas bubbles released in one of the boreholes, and these results are from the published paper by my colleague John Nyken and others. And for this part, I'm going to focus only on the hydrophone data because they are the only ones that recorded signals generated by these bubbles in the boreholes. And so here is a spectrogram showing showing about 9 months deployment period of the hydrophone data. On this spectrogram, you clearly see some vertical stripes, which means that the signals in those windows are broadband. And on top of that, you also see these kind of slowly changing those spectral peaks with slowly changing frequencies. And these are caused by the eigenresonances of the borehole, also called organ pipe modes. And if you zoom into those individual vertical stripes, you'll see that they are actually bubble swarm. They're actually caused by the impulsive acoustic signals generated by the bubble swarms. And they happened episodically, mostly at those 4 days. And here is a zoom into one of those episodes where you see this very densely spaced spikes caused by the bubbles. And since those bubbles were injected at very specific times, the authors came up with this model where gas is accumulated at some constrictions on the borehole walls, and the pressure will increase as more and more gas accumulated there. And when it exceeds the capillary pressure, all the gas bubbles are released into the borehole. That causes these episodic bubble swarms. And so these results may not seem that exciting, but what I want to emphasize that the borehole water samples from the nearby boreholes are undersaturated, or at least undersaturated at the time when they were sampled. And this is also from a published study by Alexis Templeton's group. And this is strange because we kind of see conflicting evidence about the presence of free gas in the boreholes. However, these results can be reconciled if we just assume that the gas flux in the formation is dynamic over time. I mean, so for example, here, we don't see any free gas for most part of the observation time in this borehole. We only see them at a time when the gas bubbles were released into the boreholes. And if we happen to come at any point of those time ranges, you just won't see any gas. And that has a pretty big implication because for many of the previous geochemical studies, people typically just sample the gas at one place and a specific time and then get to a conclusion. But here we are showing that clearly that the gas flux is dynamic in time and also heterogeneous in space, since the gas bubbles are only injected at one point in the borehole, not at other points.
So you don't have a long-term gas monitoring on those wells?
No, unfortunately not. Yeah, and I think the geochemists are to be blamed, but that's, yeah, so I think what's necessary obviously is continuous monitoring, but unfortunately it was not available at the MBO.
Why isn't there a bubble swarm at 300 days? Do you have a spectral feature that doesn't?
Oh, so that's due to human activity. I think that probably the field crew visited the site.
I see.
Yeah. So in the paper, they said that this spectral peak is due to human activity. Yeah, not bubbles. But at this scale, you just can't see it.
And wind and stuff like this doesn't affect anything? Wind, storms?
So this didn't correlate with any of the surface phenomena, but later on I will show the fracture swarms I'll show are strongly correlated with precipitation. Yeah.
So is that what's the type of drilling?
So this
Reverse
borehole,
circulation or diamond core?
so this specific borehole was core BA1B, but the other borehole was drilled, but this specific borehole was core. Yeah, and it's a narrower borehole. Yeah, and I think in the other boreholes they observe a few gas bubbles, but not as many as observed in this borehole. Yeah, that means probably this borehole just happened to cross-cut a major gas pathway, something. And I will talk about major gas pathways in the next part of the talk. So this is all about gas bubbles. And the second part of the talk, I will introduce my own work about the enigmatic harmonic tremor signals that we observe on the same site. And these tremors are fortunately recorded by both the geophone, surface geophone, and the borehole hydrophone arrays. So here I'm showing a 5-minute power spectrum of one of the geophones. And x-axis is frequency and y-axis is power spectral density. And on this spectrum, you clearly see these evenly spaced spectral peaks marked by these red arrows. And they are strictly evenly spaced with a frequency spacing of about 12.75 hertz. And they also have a very irregular power distribution. As you can see, some of the modes were missing. And specifically, the fundamental mode was missing, which is very weird because in the resonance series, typically the fundamental mode is the strongest. But here, we just don't see a fundamental mode. And also, there's no clear decay in energy as we move to higher modes. That's also pretty strange. And when we look at the entire observation period, we can see that this resonance signal continued for the entire 9 months of our hydrophone experiment. So on the top panel, I'm showing the 9 months hydrophone spectrogram in this very narrow frequency range of 25 to 26 hertz. This is the frequency range containing the lowest observable mode 2 of our series of our tremors. And we see this oscillating spectral lines that was on for the entire 9 months period. And this is zooming into the 21 days period in the end, where we have both the geophone and hydrophone observations. And here you can clearly see that there is a diurnal frequency oscillation that exhibited by this tremor signal. And on the left-hand side, I'm showing the 21-day period recorded on a geophone. And this is to show that the frequency variation is exactly the same between the hydrophones and the geophones, which are completely independent. They are not powered by the same power system or recorded by the same data logger. So, and the same signal also showed up on all the geophone instruments, which are all independent, which suggests that it's not due to an instrument issue. And so here I'm showing the frequency variation of all the 12 observable modes over the 21-day period of the geophone observation. And you can see that their frequency variations are perfectly correlated. And here the dark and light stripes show day and night times, so that you can see the diurnal frequency variation more clearly. And this is a very salient feature of our tremor signals. And also you can see that the higher modes, especially the ones above the fourth modes, are more clearly observed at nights than in days, although the lowest 2 modes seem to be on most of the time.
Sorry, can't tell, is the frequency higher during the day or at night?
So the frequencies, well, the higher frequency seems to be at the morning. So like this is morning from as it goes from night to day.
Okay, so gray is night.
Gray is night and white is day. Yeah. And so since all the modes frequencies are perfectly correlated, you expect their power to be 2, but that's not the case. Here I'm showing the power variation of the lowest 2 observable modes. Remember, mode 1, where the fundamental was not observed, only observed mode 2 and mode 3. And for mode 2, we see that its power is relatively stable. The y-axis is in dB log scale. But for mode 3, there is a very strong power variation on the order of 30 dB. So it's 1,000 time power variation. And also its power seems to be higher at night, always higher at night than in day. So here again, the gray and the white strips show nights and day. And that's completely decorrelated with mode 2. Here I'm showing the power correlation matrix between all the nodes that were on for enough time windows. You can see that for all the modes for mode 3 and above, their powers are reasonably well correlated. But for mode 2, it's decorrelated with all the other modes, which is strange because their frequencies are perfectly correlated. This is one of the most enigmatic features of the tremor signals. But I will later show that similar features have been observed on harmonic tremors observed on active volcanoes as well. Okay, so a major question about in any seismic signal characterization is localization. But for this kind of signal, you obviously can't pick a arrival time like you can do with regular earthquakes. And you can't even separate the different wave types like P waves, S waves, surface wave, because it's just all one continuous wave train. However, thankfully, we have a relatively dense station network, so we can measure the differential phase delays between pairs of stations. Using that, we can derive a propagation vector, which is basically the local wave propagation direction for each triad of stations, as shown here. And here, the arrow shows the local wave propagation direction, and the color of the arrows show the apparent velocity of the wave propagation. And if you put the arrows observed on the 2 arrays together, you see that they generally point towards north, although there is considerable of scattering among them. And the 2 rows diagrams show the summary of the directions in the 2 subarrays A and B. And if you look at the amplitude, you also see that the velocity amplitude or the velocity values, you see that it's generally higher in array B than in array A. And that's consistent with the subsurface condition at the 2 arrays. In array B, in many cases, the stations were built on very thin sediment or no sediment, but array A was built on a sediment layer of about 10 meter thick. And so it is very likely that in array A, what we're observing is high frequency surface waves propagating mostly in the sedimentary layer, whereas in array B, where the propagation velocity can be up to 3,000 meters per second, we are observing mostly body waves. These propagation directions don't tell us how far the source is away from our observation site. But since we observe strong energy for modes close to 200 hertz, we conclude that the source can't be very far away from the site, since these high frequency waves don't propagate very far away due to strong attenuation. Okay, so then I will show the other most enigmatic feature of our observation. That is, the propagation directions in some of the station triads appear to show a diurnal variation as well. So here again, x-axis is time and y-axis the propagation direction measured in degrees. And the three colors show the propagation directions estimated for the three components. And you clearly see that they show a very salient diurnal variation, which is obviously not due to statistical scattering. And this Rose diagrams shows a summary of the propagation directions of the three component data. They are slightly different, probably due to different components containing different waveforms. However, all three components seem to show a very regular diurnal variation, which seems to suggest that the source is moving. But remember, this source has a near constant frequency. So how could a source like this move over time? This is another big enigmatic feature of the signal we observe. Okay, so now let's face the question that is, what is the tremor source? Because it's truly this is truly strange. We're seeing some features that are very different to explain. So the first thing we need to think about is whether these signals are due to anthropogenic processes, since there have been many cases where similar signals were found to be due to human activities. For example, there is such thing called power line noise, which is sometimes observed on seismic data collected near high voltage power lines. And people think that these noise are due to the electromagnetic inductions due to the AC current running in the power lines. However, our instrument, so there's no high voltage power line near our site, and all the instruments were powered by DC. And also, we have seen that there is a clear propagation pattern across the array, and the propagation speed is typical for elastic waves. And so this is unlikely. The second possibility is that these signals are caused by transportation equipment, like freight trains, aircrafts, or even cars. However, these signals are typically short-lasting, and also the frequencies generated by these equipments typically vary rapidly over time due to Doppler effects, for example, which is inconsistent with our signals. So this is also ruled out. And finally, the most plausible anthropogenic process for generating our signal is some sort of machine with a rotating component, such as a power generator or a water pump. And in this case, the rotating rate of that machine dictates the frequency of the fundamental mode. So to look into this possibility, we actually found the signals of a diesel generator recorded on public seismic data. So the two green power spectra or spectra of seismic data recorded by two seismic instruments that are, one is very close to the power generator, DR6, and the other is about 100 meters away from the power generator. And plotted in orange is our spectra, which was the one you just saw. At the first glance, you can see that they are very different because our power spectra has much higher quality factors than the generators, which means that the peaks are much more skinny. And also the mode structure is very different. As you can see for the power generator case, when you move away from the power generator, the higher modes decay very fast. And at a distance of about 100 meters, the higher modes near 200 hertz is almost below noise level. However, in our case, the higher modes can even be stronger than the lowest mode. And to further illustrate the difference, we extrapolate the mode power to a hypothetical distance of 3 kilometers, which is the closest human settlement to our site, that farm, and using a constant quality factor of 30. And this gives us the diamonds. As you can see, if this is generated by a machine at that farm, the highest mode will be 80 dB stronger than the lowest mode. And this is completely different from the signatures of any sort of machines. So this is also unlikely. And on top of that, we also saw incoherent mode power of variation, which cannot be generated by a rotating machine, since the rotating machine, the rotating process is inherently repeating. And also, distant machine cannot generate the time-dependent propagation directions observed for our tremor. So that basically excludes all known anthropogenic processes. So we probably need a natural process for our signals. And the popular natural process that is often evoked for explaining this kind of signal is a series of repeating events that happen at a semi-regular interval. And this mechanism has been evoked to explain both tremors that happen on volcanoes and on glaciers. However, for this mechanism to explain our tremors, we'll need the repeating event to keep firing at a very high rate of about 12 hertz per second and continuously for 9 months. And that's just a highly unlikely scenario. And secondly, the repeating event mechanism can't explain the incoherent mode power variation that we observe, because again, the repeating source is by definition repeating. So the mode powers should vary coherently. And that leaves us with only one option. That is, the tremors are generated by the resonance of a fluid-filled cavity in the subsurface. And this mechanism has been evoked to explain many of the harmonic tremors observed on active volcanoes. And in fact, harmonic tremors have been, or natural harmonic tremors have been most commonly observed on active volcanoes. And here I'm showing one example observed on a volcano in Indonesia. And here the spectrogram was rotating 90 degrees. The y-axis is time and x-axis is frequency. And in this case, they also observed that the fundamental mode of the harmonic series is missing, which is also seen in our signal. And also they saw that the mode powers seem to vary independently. And you can kind of saw that in this spectrogram as well. So these two very mysterious features were actually common between our tremors and volcanic tremors. And here is another example of harmonic tremors observed on another volcano in Costa Rica. And in this case, the authors observed a rapid change in the particle motion in a very short period of time, shown by the white box. And in this case, they thought that the change in particle motion is probably due to a rapid movement of the source from deeper depths to shallower depths. And also know that in this time window, the frequency of the tremor actually didn't change much, but it apparently moved very rapidly. And this feature was also observed for our tremors. And these commonalities between our tremors and the previously reported volcanic tremors suggest that they may have a common origin. And in our case, the resonating fluid-filled cavity, we think, is probably a subsurface fracture with a continuous flow of gas through it, which lasted for an entire 9 months period, as shown by this cartoon. And on this cartoon, I'm also showing the episodic bubble releases into the boreholes reported by our previous work. And so our seismic data can't tell us how deep the fracture is, but but we think that the fracture is probably below the water level, which is at about 50 meters. And the drilling and the experiments conducted in the borehole show that we don't have much permeability below 150 meters. So we infer that our fracture is probably located in this depth range. And using this data and the resonating quality factor, we infer that the gas volume fraction is somewhere between 76% to 99%. So that's very high, because only that high number can explain the high quality factors we observed. And using the resonance frequency, we can estimate the resonance length scale of 2 to 20 meters, although that depends on the depth of our source. And finally, the enigmatic diurnal variation, we think is probably modulated by thermoelastic stress, which were known to penetrate much deeper than the diurnal temperature variation itself. And so there are several important implications of our results. First, we have shown that the gas migration in the subsurface in the peridotite formation can be both episodic and sustained, as shown by the bubble releases and our tremors. And this continuous gas flow probably represents one of those gas highways conceptualized by some of the previous works. And secondly, the free gas may be more prevalent than in this formation than previously estimated, because remember, the previous workers didn't sample any free gas in the boreholes. However, the seismic and the acoustic results seem to suggest that there is abundant free gas in the subsurface. And finally, and probably most importantly, we show that seismic techniques could offer new approaches to monitor subsurface gas flux. All right, so this is all I have for addressing our first question about gas transportation in the subsurface. And then I will move on to the second one about reaction-driven fracturing. And this work is from a paper which was just accepted by my colleague, first authored by my colleague John Nyken and colleagues. And for this work, we'll again focus only on the hydrophone data, since the fracturing happened in one of the boreholes. So here I'm showing the 4 fracturing episodes observed in borehole BA1A. And here, and the waveforms are plotted at 4 of the deeper boreholes, 4 of the deeper hydrophones in the boreholes. And as you can look, you can see each fracture is shown by one impulsive waveform. And by looking at its amplitude, you can see that it gradually migrated downward towards the bottom of the borehole. That indicates that the fracture started near the top of the borehole and then gradually propagated downward. And when you plot the number of, you plot the occurrence of those fracturing events and compare them with the water level in the boreholes, as well as the rainfall or precipitation at the site, you'll see that all of the fracturing events happen in a time period where there is elevated water level in the boreholes. Although the increase in borehole water level is just 1 meter, which was obviously caused by the precipitation. So surprisingly, it also rains in Oman, although it's just it's a desert. And so this strongly suggests that the fracturing are caused by the pore pressure increases due to this water level increase, although this increase is just 1 meter of wellhead. And another evidence we saw is that there are subvertical veins in these boreholes, which are probably filled with mostly serpentines and probably a little bit of carbonates. And those veins are probably where these fractures happened, and they provided the pathways for the fractures to propagate downward. And putting these 2 pieces of evidence together, we think that these fractures are probably tensile fractures that initiated near the top of the borehole and then propagated all the way down to the borehole bottom. And we can locate these events, which will give us a propagation speed of these fractures. And the propagation speed is in the range of 6 to 20 centimeters per second, which is similar to the rupture speed of slow earthquakes, which some of the earthquake seismologists here must be familiar with. And this interesting observation suggests that these 2 processes may share similar mechanisms. And my colleagues further developed a model of dilatant hardening to explain why the fracture propagates so slowly down the borehole. And the intuition of this model is that when a new fracture is created, or new fracture is created, the fluid needs to flow to fill the fractures before it can fracture further. Therefore, the fracture propagating speed is controlled by the fluid diffusion speed, and that cannot be too fast. Okay, so everything looks great, but there is just only one problem. Because that is the fracture seems to be triggered by a teeny tiny pore pressure increase of only 1 meter of water. That means the tensile stress at the fracture tips had to remain near critical, like two years after the boreholes were established. These kind of fractures were typically observed when the boreholes were first established within a few weeks or so, but this is 2 years after the boreholes were drilled, and all the tensile fractures were supposed to have already dissipated. But again, we saw that the tensile stress at the fracture tips seem to remain critical. And that means there has to be a mechanism that does that. And we think that this mechanism may be the growth of the alteration minerals such as serpentines and carbonates. And since this growth of alteration product can enable increase of pore pressure, such small increase in pore pressure to fracture rock, that means this process will probably also help us fracture the formation, where we try to stimulate the production of hydrogen or the sequestration of CO2 in these formations. And that's the main takeaway from this study. All right, that's all I have for today. And hopefully these conclusions are clear to you now, and I'll leave them there and take questions.
All right, thanks, Tianze, for a great talk. Do we have any questions? And feel free to ask questions on Zoom as well in the chat.
I have one, how well do we have a constraint what is actually the rate limiting step for the serpentinization, right? It seems that, if you correlate the precipitation and then you say that the pore fluids must be the thing that is causing the increased rates, and I agree that, the stress changes must be minimal. But the question is sort of how, is there maybe a chemical reactivity is kind of high to this, that you recharge the water with the fresh water that is actually reactive with the rocks, whereas the ones that is already there has kind of equilibrated with the rocks? Is that a possibility?
So we know that fresh water is being constantly supplied in this case because it rains, and also the hyperalkaline water was drained. But regarding the chemistry, I don't really have a clear idea. But one thing I know was that after draining out the hole, they measured the redox state in the water, and it was pretty oxidized or oxic because we introduced surface water into the borehole. But after maybe 1 year or so, they came back and measured the redox state in the water again, and they saw that there was the redox front that was that has propagated upward to a certain depth, and below that depth, the water again become very reduced. Mm-hmm. That probably suggests that there is active serpentinization that is supplying this very reduced fluid into the borehole.
Yeah, and it's sort of, the active serpentinization is maybe limited by the availability of reactive water.
Could be. Yeah, could be. Yes, because obviously the supply of natural precipitation is much slower than the supply of water during drilling. Yeah. And so, yeah, that could be a limiting effect.
Because it rained like 4 times over 9 months there, right?
You mean the fractures?
Yeah.
Yeah, it's if you go back, yes. So they all happen within this time range, and this is maybe 3 months.
No, sure.
And this is the time range where you have the highest water levels in the boreholes.
But you didn't have an awful lot of precipitation. Why is it going up so strongly?
You mean why this went up so much?
Yeah, I mean, it doesn't correlate with your precipitation events.
It correlated with this one.
Yeah, sure. And then it goes up dramatically. And before you have equal rises in the back in October 2019, and it goes down.
Yeah, I don't know what's happening.
I mean,
In
the
the
water table and the precipitation do not correlate.
Yeah, that's a mystery. I think there are a lot of other things going on in the formation. For example, so first the farmers may be pumping the water from the reservoir. That's one possibility. And also, like, there may be new fluid pathways being established at some point in this time range, which could drain the water. Yeah, so I don't really know why the precipitation didn't really correlate with water level, although I did notice that, but the paper didn't really provide an explanation. But these fracturing events did happen in this time interval where you have the highest water level, that's for sure. So I would say that's still a mystery, and we don't know how the fluid flow in this formation very well.
Did you use piezometry? Piezometry,
What is
where
that?
you can measure the pore pressure, like directly in the borehole.
I don't.
It's like an instrument that you.
I don't think they did, or I didn't see those results.
Yeah.
Yeah, I think.
Well, it can be also affected by human activity, but it's different than the acoustic. So maybe you can
So
test
you mean
against the acoustic.
Does it need to be put in the borehole for a long
Yeah.
time?
Well, not all the time, but you have to put it down and let it stay a bit, and then it can measure the pore pressure. It's used in open pit mines for early warning, slope failure, and so it measures the pore pressure.
Yeah, I don't remember seeing those results, and certainly they were not there for a long time. Yeah, I don't think there is any time continuous observation in those boreholes other than our hydrophones, which is it's a pity. And one of those boreholes is already, developed by a carbon sequestration startup company, so you can't return to it anymore.
And do you have is that the core?
This is a televiewer, so they essentially put a camera down the borehole to collect the optic image of the borehole walls.
And you have the core.
Yeah, we have the cores. Yeah.
Can you compare the fracture network and the core with the wall if it changed?
I don't think they did it.
And is the core oriented or just
I
standard?
think.
Sorry, guys, can I chime in here? These fractures were in.
He probably knows more about the other results than me. Can I?
The volume is on the control on the side.
Yeah.
I just want to clarify that.
Wait a second, Rob, we don't hear you yet.
Okay.
Now try again.
Hello?
Yeah, now we hear you.
Okay, sorry. I just wanted to clarify that these downward propagating fractures were observed in borehole A, and that's where you see the Keller viewer data. But that hole was not cored; it was drilled. So there were shadings extracted, but no core.
No, yeah, but that's what we have.
So both drill holes are now being used by some company. I mean, wouldn't that be a great place to put a few of those geophones down and a GC on top of it and see how it correlates?
So I think that the entire site is developed, our site, but I believe there are a couple more boreholes away from the site. But our specific site is developed, and if you look at the satellite image collected maybe very recently, you will see basically an infrastructure on top of it, and that was not there when we collected it.
And you guys must be not the only seismic network that exists in Oman. Did you look into existing network? Have you see similar phenomenon, or is it not the right spacing?
We did see resonance signals in other. So there is a seismic network deployed by the GFZ scientists, like in 2016. But their station spacing is very large because they were looking at crustal and the lithospheric structures and look at their data, and many of them did contain these resonance signals. But since they are stationed very far away from each other, they don't report the same resonance signals. But many of them did contain resonance signals. Since the signals I just showed you are very high frequency, they don't propagate very far away. You have to be sufficiently close to them to be able to observe. Yeah, especially for the most up to 200 hertz. It's very hard to observe them at long distance. But many of those stations did contain resonance signals. But again, for those signals, it's hard to definitively say that they are not from anthropogenic processes, because some of the stations were deployed close to houses or towns. Some of them were even put in like the school backyards. So, we can't really differentiate. Sorry?
You see the recess.
Yeah, right, probably. Yeah, but for our side, we are very confident that these signals are not due to anthropogenic process, due to all the evidence I showed you.
And your data, can you use your data to say something more definitive about the gas production flux in these things that you sort of started off your talk with? It's kind of difficult. So for the bubbles, you can measure the bubble sizes, because so the bubble is resonance as well, and the resonant frequency is controlled by size. So we can measure the bubble size, but still that's just one bubble, one gas pathway. I don't know how you can generalize that from there. And so I can quickly show you something that I saved in case we have enough time. So there are some earthquake seismologists here, and so nowadays people are interested in small seismic events, and we did see the quote-unquote small seismic events within our arrays. This is the heat map of them. And what's interesting is that they're clustered in some very limited, narrow areas that are just a few meters by a few meters. And so the scale here is log scale. So there's a very high event density. And also these events it contains large number of similar waveforms, which suggests that they happen probably exactly at the same location, because the cross correlation values can't tell them apart. They are all the same. You can't measure, you can't relocate them, because they are all perfectly aligned, suggesting that they are almost perfectly co-located. And here is another example observed in the different subarray. And what's more interesting, that their occurrence seems to have an anti-correlation with the power of the tremor. So the lower panel shows the mode 3 power, the one you saw before, and top I'm showing the occurrence or event rate of 3 event groups. And the blue ones happened within array A, which is is closer to the tremor source. And we see a very clear anti-correlation between the event rates and the tremor power, suggesting that they may be physically connected. And our tentative interpretation for these small events is that they probably represent very transient degassing in the subsurface. These events are probably just a few meters deep. And since these are just gas pathways, they remain at the same location, right?
Yeah. I don't know, it's after 1 p.m, so if anyone needs to leave, then feel free.
Yeah.
I do want to also ask, there's a couple of questions on Zoom. Jean asks if there were any active seismic monitoring or cross-well seismics that were done.
No, so the measurements done at the site is quite limited. It's not up to industrial standard, I would say. This is purely scientific, and I think it's pretty amazing that they got this project funded.
Do you think you would be able to detect gas pockets if you could do an active survey?
Gas pockets?
Like pockets of the gas in the subsurface with active methods?
Yeah, I think so. Yeah, and also there's nothing special about this site. It's just in the borehole formation. And I don't think anything we see here is specific to this location. Yeah, so we should be able to see this in other ophiolites as well. Yeah.
And one other thing, Doug, is, and this was something I was wondering as well. So these seismic events are very concentrated around where the wellheads are. And he's wondering if they could be like seismic surface waves generated at the wellhead. Or is it more just a factor of the, like, you're centered in the middle of your...
No, so it's indeed related to our detection ability, because we have stations, sensor stations near the wellheads, but these similar waveforms are also recorded on other stations, but those stations are further apart, so different stations don't record the same events. It's the same, it's like you have to be close enough to these events to record them. So we are pretty sure that these things also happen at other locations of the array. It's just that we don't have dense enough stations to see them. Yeah, if we had the same 5 meter station spacing everywhere, we should be able to see much more of them. But they still are concentrated because, like say, in one of those stations, we'll also see repeating waveforms. But it's just that this is only shown on that station, not on nearby stations. So we can't associate them into events. Yeah.
Right, one final question.
Yeah, I wasn't sure about the causality between the characteristics of the tremors and the picture that shows the rainfall. So if you go back to the slide with the rainfall, this one, yeah. So the tremors and their characteristics that you well described, were they the same prior, after?
The tremors?
Yeah. The characteristics of the tremors. I mean, it's because you looked at number of attributes of the tremors, right?
Yes.
So have they changed due to what happened at the rain?
No, I didn't see clear association between the tremors and precipitation and other events. And we all even look at the major earthquakes. Like we know that major earthquakes can perturb the stress state locally and even change the property of an aquifer, but we just didn't see any change in the tremor property associated with those factors. The only association or correlation we saw is with temperature. That's the 24-hour diurnal cycle. But there is indeed some, well, this figure is kind of, I think I can read. So, oh, there we go. So it's kind of hard to see here, but there are some, like here, you can probably see that the frequency shoots up. And this is certainly not part of the 24-hour cycle, but we don't know why it happened. We didn't see anything that happened at that time which could have caused this. But it's very enigmatic. And there seems to be a general decreasing trend in the frequency, which is also, we don't know why. Well, the only thing we know for sure is that this is not due to human activities. Yeah, and the 24-hour periodicity is pretty salient, and it's likely caused by temperature variation on the surface, and is physically caused by thermoelastic stress because temperature itself doesn't penetrate very deep.
Wouldn't you expect a difference between summer and winter? I would expect that there's quite a bit of temperature difference in summer and winter in Oman.
No, that's a very good question. Actually, I have figured it here, but I can't show it. So it seems like it's only the two things are only. Oh, actually, I have the backup slide. We did the spectral analysis between these things. I think I can show. It's slow. Let's look at this. So basically so the yellow curve is the frequency variation. So this is the spectral analysis of the frequency variation. The yellow one is the frequency variation, and the blue one is the temperature variation. And we see that they all have these diurnal and semi-diurnal, and I don't know how to say this, but 3 times a day peak. And then we can do a cross-spectral analysis, which shows you how coherent they are. And this
Is the time interval on the horizontal axis here?
Sorry?
For the temperature, is there time on the horizontal axis? What are you plotting?
It's frequency.
Oh, frequency.
Frequency. So one is here. That's diurnal. This is semi-diurnal, and this is 3 times a day. And this is the coherence between the two variables. And you see that it's only coherent at diurnal and semi-diurnal, etc. cycles. But at a longer time period, here this is 50 days. This is the longest interval we have, and they are not well correlated. So that means at longer time interval, there may be other factors that's controlling the frequency, so that overwhelms the temperature effect.
But 50 days, in which season is this taken?
It took 9 months, so it crossed the 3 seasons, I guess. Yes.
Sorry, what was the temperature again?
I mean the absolute temperature. I don't know that off the top of my head. Maybe so it's a desert, so maybe 20, 30 degrees Celsius. It's pretty hot. And also one thing that I think promoted the thermoelastic stress is first it's desert, so there's a very strong diurnal temperature variation. And also the surface is dark gray, so that absorbs radiation really well. So what we're doing here is the air temperature, but it's not the surface temperature. And we expect the surface temperature variation to be much more extreme than the air temperature. Yeah.
All right, that's all the time we have for, but thanks again for the fantastic talk and really interesting work. And let's thank you.